Hi class, we're on our last lesson from chapter 10. It's 10-6 day 2. We're talking about exponential growth and decay. Yesterday we did their graphs. Today what we're going to do is actually word problems that use exponential growth and exponential decay. Let's review again what their graphs look like. When it's exponential decay, it means that my base number is a number that's greater than 0 but less than 1. So it's in between 0 and 1. When it's exponential decay, as my x's get larger, my y's get smaller. Okay, so it gets less as it goes down and to the right. Okay, so this is exponential decay. When it's exponential growth, it means that my base is a number that's bigger than 1, which means as my x's get larger, so too do my y's get larger. And it grows exponentially, which means it has that curve in it. Okay, so those are growth and decay. Your base on these problems are always going to be between 0 and 1, or always going to be a number that's greater than 1. It will never equal 1. Your base will never equal 1. Here's the reason for that. Students ask this all the time. If you have a base of 1, well, what's 3 raised to the first? Sorry, what's 1 raised to the first? What's 1 times 3? It is 3. Okay? So what happens if what happens if 1 is squared? If x is 2. 1 squared is 1, and 1 times 3 is 3. Same thing if you were to do 3, 4, 5, 6, and 7 for x, you would constantly get 3. This is not an exponential problem. This is a constant function. It's a linear constant. So if that's the case, this is not exponential, so your base will never, ever be 1. Students also ask, Mr. Berge, how come the base can't be negative? You will never have a negative base, because look what happens if you do that. If you put 1 in here, a negative 2 raised to the first is a negative 2, and a negative 2 times 3 is a negative 6. Now what happens if you square a negative 2? Okay, so a negative 2 times a negative 2 is a positive 4, and a positive 4 times 3 is a positive 12. That's how they get this. And you see how then we get negative, and then positive, and then negative, and then positive. It alternates going from negative to positive. So you end up getting a graph that looks kind of crazy like this. This shows neither exponential growth, nor does it show exponential decay. So our base can never ever be a negative number. So it's always going to be positive, and it's always going to be bigger than 1 or less than 1 and greater than 0. Okay, this is going to be a huge part of this lesson, class. It's very important to have these formulas not memorized, but at least know how to use them. I'm going to give them to you on the test, so don't worry about memorizing it, but you do need to know what each of these variables mean. Okay? The first one I want to define here is A. It is the initial amount. Okay, so whatever you start off with, that value is A. The rate, or that R, is the increase. So if it increases by 70%, or if it increases by 3, whatever the case might be, that rate of increase, that's where your base is. The exponent is our time variable. Okay, so it's time t. And then I'm lastly going to define this y one. This y is a little bit harder to explain. It's the amount at time t. So it might be, I kind of think of it as the ending amount. So such as, you know, what's the population after 7 years? Or how much money is this worth after 20 years? Whatever the case might be, what's that ending amount? That's our y value. Okay, so for exponential growth and exponential decay, as you can see, the formulas are the exact same. This is our exponential growth formula. This is our exponential decay formula. The only difference, class, is where the rate is going to be. Remember, the rate here is always greater than 1. The rate here is always a number that is less than 1. Our rate is always going to be less than 1, but greater than 0. I'm going to talk about that as we go further with these problems. So here's what we have. Our first one. In 1985, there were 285 cell phone subscribers. There wasn't a whole lot of cell phones in 1985. I was born in 1986, and I didn't see a whole lot of cell phones until I was in like high school or so. So this was in the town of Centerville. The number of subscribers increased quite significantly by 75% per year after 1985. They got to be very, very popular. So now how many cell phone subscribers were in Centerville in 1994? Well, if you look at this one, let's define each of our variables. A is the initial amount. How many cell phone subscribers were there initially? Well, in 1985, there were 285. So 285 goes in for A. What is our rate in this case? Our rate is the percent that it grew, which is 75% each year. So now I ask you, is this growth or is this decay? It grew by 75% each year. This is hopefully quite clearly to you a growth problem because my rate is bigger than 1. Now class, as a percent, 75%, we have to write this in a decimal whenever we put this into our equation. So it would be 0.75. Now 0.75, look at this number. If you were to have this as a rate, is this number greater than 1 or is it less than 1? Hopefully you say it is less than 1, but exponential decay has to have our rate being greater than 1. So here's what we have to think of this as, class. 100% of the people in 1985, this 285 here, in 1986 they still had a cell phone. In 1987 they still had a cell phone. In 1988 they still had a cell phone. So 100% of the people who had cell phones still had it, and then it grew by 75%. So what is my rate of increase? What is my R value? You add these two to get 1.75. So to always remember this, class, whenever you need to get the rate of increase, you add it to 100%, or you add 1. What is 1 plus 0.75? It is 1.75. In the same way, right here, we get 1.75. So that's what you need to remember, class, as you do the rate, is to always add it to 1 when you do exponential growth problems. So your rate is 75%, so it's 1.75. You got to add it to 1. That's raised to the t. How many years had passed from 1985 to 1994? So from 1985 to 2004, if you subtract those two, you get 9 years. So after 9 years had passed, what is your amount at time t, or what is your amount after 9 years? How many cell phone subscribers are in Centerville in 1994? So hopefully this equation makes sense to you. Now class, all you have to do is put the rest of this in your calculator. Okay, this is the only work that I need to see for this problem. I want to warn you about something that students do wrong all the time, is they multiply this and then they raise it to the 9th. That is incorrect. You will get the wrong answer. You have to follow order of operations. Order of operations say that you do exponents first, and then you multiply by 285. So do that exponent first. 1.75 raised to the 9th. So in your calculator, 1.75, raise that to the 9th power, and you get 153.94. 153.94. 153.94. That number now multiplied by 285. And that gives you the amount of cell phone subscribers in 1994. How many people had a cell phone in 1994? Times 285. There were approximately 43,870, we'll say 2 people. We'll round to the nearest person. 43,872. 43,872 subscribers. Quite a difference, class, of 9 years, isn't it? Technology really increases exponentially because when something is found out to be good, not very many people have it right away, but as it grows and grows, it grows exponentially, and then it grows quite quickly, all the way to 43,872. Very interesting. Let's try this next one. The population of a city is 1 million people. Okay? It is increasing, so it's even getting bigger and bigger and bigger. It's increasing at a rate of 3%. If the population continues to grow at this rate, how many years will the population have doubled? So in this one, class, birth rate and death rate, very interesting concept. In this community, people are being born at a faster rate than people are dying. Okay, so we're going to have a growth rate on this one. It's going to be exponential growth where our rate is greater than 1. So let's start off our initial amount right here, class. How many people does this city have? It has 1 million. So we're going to write 1 million for our A value. The rate, it's going to be growth, so you know it has to be a number that's bigger than 1. It's 3%, right? So at 0.03 is our decimal. You have to add this to 1. So 1 plus 0.03 is going to be our growth rate, or our R, so 1.03 goes there. It says if the population continues to grow at this rate, in how many years, this is our variable. How many years? Well, years is our time t. So our t variable is what we want to find. That equals y. When will the population have doubled? Well, we can know this, class. When will the population from 1 million double to 2 million? Right? That's our amount at time t, which is what y equals. So in this case, we know y. Y is 2 million. When will it double to 2 million? We want to find this letter t right here. Okay? So here's how we solve this one. The first thing we have to do is we need to get this part all by itself. Okay? So let's divide both sides by 1 million. Okay? We'll divide the whole thing by 1 million, and then we'll get rid of it from the right. So what do we have on the right side now? All we have is 1.03 raised to the t power. That equals 2 million divided by 1 million is just 2. So 2 equals 1.03 raised to the t. So now we need to solve for t. Hopefully this looks familiar with what we've been doing in the past couple days. If I want to solve for an exponent, I got to use logarithms. So I'm going to take the log of both sides. The log of 2 equals the log of 1.03 raised to the t. So if I take the log of the left side and I take the log of the right side, I am still following math rules. Everything is good to go. We're going to use the power property to move this down in front. So now it's going to be the log of 2 equals t multiplied by the log of 1.03. All right, now how do we get t all by itself? Well, right now, this is a multiplication problem. So if I divide both sides by the log of 1.03, if I divide both sides by the log of 1.03, I get my answer. T is what? Log 2 divided by log 1.03. Calculators, we need you. The log of 2 divided by the log of 1.03. Our answer is how many years? Approximately 23 years. Approximately 23 years. Round to the nearest year again. T is approximately 23 years. So, class, I ask you this question now. What is this telling you? In about 23 years, the population of Centerville will double. Now, if you're interested in a career of administration some way or another, if you were a mayor of this community, how would this impact you? Well, you'd think, man, I need twice the number of restaurants, I need twice the number of stores, I need twice the number of hospitals, I need twice the number of schools, I need twice the number of parks in just a short 23 years. Okay, this exponential growth, exponential decay is very, very impactful in our everyday life, and it matters. Let's try another problem where we might have exponential growth. In the year 2000, Nigeria had an estimated population of 127 million. So here's this country. It has 127 million. The U.S. at that time had an estimated population of 278 million. So we were over twice as large as far as population is concerned as Nigeria. Now, Nigeria's population is projected to increase at 2.6% each year, while the United States population is projected to increase at 0.9% each year. When will Nigeria's population be more than the population of the United States? So here's what's happening. The U.S. has over twice as many people. However, Nigeria is having children at a faster rate than we are having children. So their population is increasing faster than ours. So when will their population be bigger than ours? What we're going to use, class, is we're going to use our exponential growth because both of our populations are increasing, which is A multiplied by R raised to the T. So when, let me erase this for a second. Here's how we're going to set this one up. Here is the United States. Let's do this instead. Here is Nigeria. And here is the United States. Right now, the United States population is bigger, but when will Nigeria's population be bigger? We want to find when is Nigeria going to be greater than the U.S. as far as population. Well, we're going to use our formula of A times R raised to the T. So our initial amount of Nigeria is 127 million. So 127, I'm not going to write all those zeros, I'll just write 127. Okay, know that we're talking about in the millions. Multiplied by the rate, what's the rate of Nigeria? It's 2.6, so as a decimal it's 0.026. Add 1 to that, 1.026. So 1.026 raised to the T power. This is what we want to find. We want to find how many years. Okay, so when will that be greater than the U.S. initial population is 278 million, multiplied by the rate, which the rate is 0.9%, so 0.9 as a decimal, you'd move it over twice to get 0.009. Adding 1 to that, the rate of increase is 1.009. 1.009, and that number raised to the T. Okay, so this is our equation, and what we have to do is we have to solve for T. Basically, you're just going to trait this greater than sign just as if it were an equal sign. We're going to solve for T. So right when you get to here, class, here's what I would recommend doing first. It's kind of confusing, but after you do it once, hopefully it all makes sense. This right here is a product. Okay? So when it's a product, if I take the log of both sides, why don't I do that first? The log 127 times 1.026 raised to the T is greater than the log of 278 multiplied by 1.009 raised to the T. Once I take the log of both sides, because this is a product, I can split these two up using the product property and add their logs together. So I'm just going to basically put a plus sign in between here when I have the log of both of them. So write this down with me. The log of 127 plus the log of 1.026 raised to the T. Okay, that is greater than the log of 278 plus the log of 1.009 raised to the T. Okay, so hopefully that makes sense. All I did was use the product property, okay, to split those up using addition. So once I have that, let's change some of these into numbers that we can actually quantify. It's hard to think of a number of the log of 127, but let's put that in our calculator. The log of 127 is this number, 2.1038. 2.1038. So 2.1038. Okay. What is the log of 1.026? What is the log of 1.026? That is 0.01114. So rounding to 4 decimal places is 0.0111. So I'm going to write that down. Plus. Now class, watch as I use this power property. This T could come to the front because it's an exponent, so I could bring that to the front. So it's T times 0.0111. Okay? So that's going to be greater than, let's put the log of 278 in our calculators. Log 278, round to 4 decimal places. 2.444. 2.444 plus, once again, I'm going to move the t to the front, so it's going to be t multiplied by the log of 1.009. Log 1.009. And I get 0.0039. 0.0039. 0.0039. So now, class, as weird as this might look, it's actually a pretty simple algebraic equation now. Okay? I have t's, 0.0111t, 0.0111t, and 0.0039t. I'm going to get all of my t's to this side. So I'm going to subtract 0.0039t. Subtract 0.0039t, and now that's out of the left side, so it's going to be 0.0111, 0.0111, and I'm going to subtract, the other one was 0.0039 minus 0.0039. And that's going to give me the t's that I have, 0.0072. So I have 0.0072t, and now I'm going to subtract 2.1038 from both sides. Subtract 2.1038 from both sides. So 2.4444, right? There's 4 fours. And I'm going to subtract, 4440, I guess. And I'm going to subtract 2.1038. 2.1038, and I get 0.3402. Greater than 0.3402. Whew! And lastly, I want to get my t all by itself, so I have to divide by 0.0072. Divide by 0.0072. So now, the time that we have all been waiting for is, when will Nigeria's population be bigger than the U.S.? 0.3402 divided by 0.0072. And I get, in how many years? Approximately 47 years. Approximately 47 years. So to answer this question, this was taken in 2000. So in the year 2047, in the year 2047, if the population increase stays the same, Nigeria's population will be greater than the United States population. And once again, class, this is a big deal that affects not only that country, but it affects the worldwide. The reason for that is because if it's maybe a nation that's in poverty that's growing so fast, with more people, there's got to be more goods and more resources, so on and so forth. If there is battling nations that are at war with each other, more people oftentimes means more power and stuff like that too. So this is these type of problems really affect our everyday life. And it's stuff that we have to need to know to prepare for the future. Those are some exponential growth type problems. Be sure to let me know if you have any questions on those.